Good morning, I'm Pete Schrader, and we'll be talking about poker and machine learning and applications in game theory. A little bit about myself: graduated from Michigan State in 2009 with a degree in political science. After that, I flew helicopters in the Marines for almost 10 years. I'm currently pursuing a master's in international relations and economics from American University and continuing my professional development as a data scientist. A little bit about poker and game theory. Two major types of games in game theory are perfect information games, examples being chess, checkers, and tic-tac-toe, where the boards for this game are visible to everyone and there's no hidden information. Texas Hold'em, which is a variant of poker, is an example of an imperfect information game. That is, you do not know the other player's hand, so there's hidden information. And in games like this, there's no single dominant strategy that ensures you win every time. This leaves an opportunity for machine learning to strategize for a reward maximizing play. For the environment, I chose to train my agent to play poker. Use a simplified version of Texas Hold'em. In this game, each player gets 2 cards. On the right there is an example. The 2 cards on the bottom, the aces, are our cards that we know, and the 2 cards that are facing on the top are the other player's cards that we do not know. There's also 3 community cards. Those 3 cards in the middle on the right there, those cards every player can see, and you combine those with the cards in your hands to make your best possible hand. For this game, each player gets 2 possible moves, or gets 2 rounds of moves. The first one is based on their hand cards and the community cards, and then the second round is based on, or is in response to other player moves. The possible moves that you can make are check or call, in which a player just wants to stay in the game without changing the bet, or they can raise if they feel they have a strong hand, they want to bet more money, or they can fold if they feel their hand is too weak to even win and they just want to get out of the game early. And the winner is determined by who has the strongest hand of the remaining players at the end of the hand. I started with some fixed strategy analysis to kind of set a baseline. I simulated 3-player games with 10,000 hands each. For the 3 players, I had one hawk, which was an aggressive player that would bet on a bad hand. I had a dove player, who's a conservative player who would not bet unless they had a good hand, and one random player that just made random moves no matter what cards they had. In the 3-player games, the hawk clearly was the best strategy that won the majority of the time. However, when I added complexity, as I added a 4th player, there was no clear winner. All strategies kind of converged with no one really standing out. This led to an opportunity for machine learning to improve on the strategy. Specifically, the algorithm I used was deep counterfactual regret minimization, which is a form of reinforcement learning. With reinforcement learning, it's an algorithm that tries to maximize a reward based on strategies. For the deep counterfactual regret minimization, the key there is regret minimization. It's trying to minimize losing. And the way that works is it starts with a game state, which is all of the cards in play plus the player moves. And then based on that state, it traverses a game tree. We have an example of a tic-tac-toe game tree because it's a simple example. Basically, it's a tree that maps out all possible moves and outcomes. Once the algorithm traverses the game tree based on the state, it assigns probabilities to various moves and then makes the move that maximizes the reward. The reward is determined at the end of the hand by who won. If the player won, the positive reward. If they lose, they get a negative reward. And again, the goal is to minimize losing. This is the specific CFR agent that I trained. It played against and learned against other pre-trained AI agents. This was over 750,000 hands. You can see that it improved performance, starting with a negative reward and leveling off at about a 0.4 positive reward. It did average a positive reward over the course of the hands, which indicates that it wins more than loses, and it was a clear improvement over fixed strategy. This is a program with a further simplified version of Texas Hold'em. It allowed me to actually upload my specifically trained agent to play against another AI agent. In this case, each player gets 1 card and there's 1 community card. You can see on the right there, the algorithm is updating probabilities of the different moves it should make to try to maximize winning the hand. And you'll see here, game ends. It's not clear, however, the player at the bottom, player 1, which was my agent, actually won. Further applications of this, I'd like to take real-world poker data from actual tournaments and apply another algorithm called long short-term memory to identify player trends and sequence of bets. It can also use image recognition to identify tells for when a player is bluffing. It can also apply to other real-world imperfect information situations, specifically in international relations when dealing with international business negotiations or trade deals in which you do not know the information that the other player has, but you can find a strategy that maximizes your chance of a positive reward.